Alright, so before we get into move semantics, let's talk about the different value categories. So in C++, we have several different value categories, and expressions can fall into one of several of these categories. There's more than just L values and R values. There's also PR values, X values, GL values, and a couple others. But these are the main ones, and most expressions can fall into one of either of these categories. So in general, an L value is an expression that you can take the address of. Okay? So for instance, if I declare a variable, just say int x, then later on I could do ampersand x, and that would give me a pointer to x, because when the compiler sees the declaration of int x, it says, okay, I need to allocate some space on the stack for that variable, right? It's a stack variable. So then int x, so x lives on the stack. And you can take the address of x, and that makes sense. Alright, so all is well. With R values, on the other hand, R values are things like literals. Okay, they're temporary values. You can't take the address of them because they don't really live in memory. Okay, if you were to disassemble your program, then you'd see that if you're assigning a literal to a variable, okay, then the literal, it doesn't live in memory. Okay, you just put it directly into some register. Okay, and then you have a store instruction which puts the value of that register into the variable. Okay, but in general, R values are things that you can't take the address of. Okay, so pointers to R values don't always make sense. Okay, and strictly speaking, R values can have addresses. So if you have temporary objects, like a temporary class or a temporary structure, then you can't always fit classes or structures into registers. Sometimes you have to allocate space for them on the stack. So the compiler will make that distinction. But the important thing to note is that R values, well, if you can't necessarily take the address of it, then it's probably an R value. So the important thing to note here is I said literals such as 1.0f or 3 would be considered R values, but string literals are not considered R values. So when a compiler sees a string literal, what it actually does is it goes off to the data section, it writes some string there, and then it comes back to the code section, and wherever you use that particular string, the compiler inserts a pointer to that string. Okay? So if you remember from C, arrays decay into pointers. A string literal is really an array of characters, so that will decay into a pointer to a character array. Alright. So let's talk about R value references. So previously, in old C++, you could only declare references to L values. You couldn't make references to R values or references to temporaries. And this kind of makes sense because the primary reason you use references is if you want to access or modify some variable outside its scope. Okay? So for instance, you might have a function where you pass a reference to a variable, and then you can modify the variable that you pass it, and that variable will get modified in whatever scope it's declared in. But you might, if you have an R value, for instance, you pass a literal to a function. Taking the function accepting a reference to a literal doesn't really make sense, okay? Because why would it want to modify a temporary, something that's about to be destroyed? Well, as it turns out, there are situations where modifying a temporary does make sense, and it's actually preferable for the sake of efficiency, among other things. So C++11, long story short, it introduces the capability for you to differentiate between temporaries and non-temporaries. So you have access to R value references. Okay, so one important thing to say is that R value references, you don't really hear the term that much outside of certain programming idioms, namely move semantics and perfect forwarding. So just something to note. All of this is to kind of preface move semantics and perfect forwarding. So let's talk about move semantics. So I have an example on the right side of this slide. So I have a class called foo. On construction, foo instantiates a new bar object, stores the pointer to that bar object as a member variable. Okay? The destructor of foo If bar is a valid pointer, then it destroys that bar object. So then we have an assignment operator. Okay, the assignment operator takes a const foo ref on the right side. If the bar pointer of the current foo is valid, then it destroys that bar object. After that, it then copies the bar object from the other foo. Okay, so it instantiates a new bar object, passing to the copy constructor of bar the other bar from the other foo. Okay, so what is the problem with this code? Okay, so this presents a problem if we try to do the following down here in main. Okay, so let's look at main. So what we do here is we create a new foo object, f1, so that the compiler allocates some space on the stack and then invokes foo's constructor. Foo's constructor instantiates a new bar, and then it returns, and then it proceeds with our code. So then here, presumably we do some kind of operation involving the foo, whatever, some important calculation, and then we get to this line. And this line is where things get interesting. Okay, so look at what's going on the right. So we're creating a new foo object. Okay, it's a temporary foo object. The temporary foo's constructor will create a new bar object. Okay, and then the assignment operator gets invoked. The assignment operator sees the temporary foo on the right and says, okay, I've got to copy the bar object from that temporary foo. Then the assignment operator finishes copying, and then the temporary foo immediately gets destroyed. So hopefully you can see that this is a very inefficient way of reassigning a foo object, okay? Because we have a temporary being needlessly created and then destroyed, and then between creating and destroying it, we copy its data into another foo, okay? So really this doesn't make any sense. If we could somehow steal the bar object being created in the temporary, or just construct the bar object directly in place in F1, then this would obviously be preferable to what we're doing currently. Okay, so obviously this situation that we have is very inefficient. So with access to R-value references, we can actually alleviate this inefficiency. Okay, so take a look at what we have going on here. So now what we've done is we've overloaded the assignment operator, and the assignment operator now takes a foo R-value ref. So what this means is we can now differentiate between a foo that's a temporary and a foo that's a non-temporary. Okay, so what we're doing in the overloaded assignment operator, we steal the bar pointer from the other foo, okay, and then we nullify or invalidate the bar pointer in the other foo. Okay, so what we could now do, we could use our assignment operator now on a temporary foo. The temporary foo's bar pointer will get stolen, and then the temporary foo, when it's destroyed, the destructor will just see a null pointer and just go ahead and return. Okay, but now we don't have the needless copy. Okay, which is kind of wasting our time before. So the reason we couldn't do this before, okay, is we couldn't differentiate between a temporary foo and a non-temporary foo. Okay. So it's important to say that there would be situations, beforehand where you would want that original assignment operator. Okay, if you're assigning from a foo that already exists, then obviously you'd want to copy rather than stealing the resource, because then you'd steal the pointer, and then you might have undesired behavior or undefined behavior at some other point. So you can apply the same concept to the copy constructor. Okay, so let's say you invoke the copy constructor of foo with a temporary foo object, just like we were invoking the assignment operator with a temporary. Okay, so now what we can do is we can very efficiently just construct a foo from a temporary foo, okay, and just steal that other foo's bar pointer. Okay, and that's exactly what we're doing here. We're just setting our bar pointer equal oh, I'm sorry, we're just setting our bar pointer equal to the other bar pointer, okay, and then nullifying the other bar pointer. So it's the same kind of thing we were doing in the assignment operator, okay? But we still have our original copy constructor, so if we're not past a temporary, we can still handle that situation where we can say, okay, we do actually need to copy, so let's copy. So this is much better than the situation we had before. So if the compiler sees you passing in a temporary, it will select the move constructor. If it sees you passing in an L value, it will select the copy constructor. So let's talk about STDMove. So STDMove is an important part of the STL when we're talking about move semantics. So the important thing to note is that STDMove, it doesn't actually move anything despite the name. What it actually does is it safely casts an L value to an R value if you have an L value that you want to treat as an R value. Okay, so take a look at this example code that we have down here. So what we're doing is we're instantiating a foo object f1, okay, and then we're instantiating another foo object f2, and we're passing f1 after we've casted it to an R value. So f2, when f2 is constructed, the move constructor of foo will be selected, and what will happen is f2 will steal the resources from f1, and then the pointers in f1, the pointer that we have to the bar object, will be invalidated. So you can use this if you have a situation where you're going to be no longer needing an object and you'd like to, make a copy of it or move it to a different object. What this also allows you to do is have a concept of ownership. So what you could do is you could have a class where the copy constructor and the copy assignment operator are deleted, and then you can only have the the move constructor and the move assignment operator. And then what you have is you have a class that can only be moved and can never be copied. So what you essentially have is you have a class, and that class is only going to exist in one place. You're going to only have one copy of that class. You can transfer ownership of that class if you need to do something with it somewhere else, but you can't copy it. And the STL uses this in several places. It uses it in STDUnique pointer, which is part of the memory library, okay, smart pointer. So STDUnique pointer, what it does is it basically allows you to have memory allocation happen on construction, and then a memory destroy happen on destruction, okay? And you can only have one copy of that unique pointer object because, it's called unique, so they've deleted the copy constructor and the copy assignment operator, so you can only move it. So you can only have one unique copy of it.